structures. Okay, everyone. Today we'll be studying about how to draw CMOS structures, few CMOS structures using this design schematic of the MicroWind software. Okay. So first, in the previous lecture, we have studied about what are these palettes like. Here we have like a save button, save and open button. Then again, there are few buttons like this is a button gun which you can find. It is a use for cut. If you don't want any of the module or any of the design part, you can remove that one. And this is for copy and paste button. And here you can see these are the flips. We can make a turning of the rotating of a particular transistor in any of the direction, from right to left or left to right. And this is a flipping of the transistor, like terminals will be changed from vertical flip will be taking place, and this is for the horizontal flip. And this is one which we use for naming of that anything if you want to name in that particular design. Once after drawing the diagram, if you want to put a label for the diagram, we can use this one, capital A. And this is a line. Yesterday we have seen that in the previous lecture, that this is used for making the connections, line connections. And this one you can see it's a connector between the lines. If we'll be using whenever we use different kinds of advanced level of designing, we'll be using this one. And the next one, this is a simulation button which runs your entire circuit, and this is a timing diagram. And here, once if you click the all, the entire design which are your designed here will come into one single page. So that is all. And maximize and minimize, zoom in, zoom out are there. And these are the logics which you use. This is the palette one which you find here. This is the one. If you click upon this one, you can obtain this palette here. So now let us start this one. And our top, you can find a few more options like file, where you can go and resume to your previous design, or else you can go with the new window and you can start new designing. And this save and save as, and foundry is nothing else but it talks about the technology, what kind of technology you want to use. But as of now, since it's a student version, we don't have any kind of foundry here in this one. And make Verilog file. Once if you try to design any of the CMOS structure, you can directly obtain the Verilog code for that particular design. So again, even you can even obtain the spice file also. You might have studied about different kinds of spice tools like LT spice, T spice, and different kinds of spice coding languages are there. You can obtain the spice file for that one also. And okay, schema, new symbol, and everything will be obtained. And monochrome is you can, whatever the color you find here. This, if I click upon monochrome, it completely turns your complete window interface will change into a white color. So that's a monochrome. And next, in edit, we'll be having many different options like undo, cut, paste, copy, and different kinds of that. Same thing, whatever you find here, I have kept upon this window here. Rotate left, rotate right, flip horizontal, and flip vertical, line, connect, and text. And insert, in the insert, we can use different, if you have designed any kind of structure previously, that structure can be, you can call that structure into this present window, and you can use that one also. And these are the timing diagram, and this is regarding the some electrical net and timing diagrams. That's the obtaining of the outputs and everything. And this is a palette, symbol palette, which you find here, and all these options are given here. And this is exclusively for the simulation part. So start simulation and simulating options are there. Few simulating options are there. You can even customize that simulation how you want that particular circuit has to be simulated. Depending upon your customization, you can customize this one. And in the help, we can, okay, this is regarding the manual of this particular software. So now let us start the designing of CMOS buffer first. CMOS buffer. We know buffer is nothing else but here. Buffer is nothing else but this is a logical structure I am putting here. This is an inverter. If I try to put inverter, that's it's a cascading of inverter. So now if I try to stack this inverter with this one, then this entire setup we call it as a buffer. So now This is an input which I have given, and output I'm trying to put it. And in the previous lecture, I studied that how to um, bring this all the components from this palette to this one. You are supposed to click on your left click of the mouse and drag it onto this window. Then you can try to bring this one from this one. See now, I don't want this AND gate here, so I can use the cut one. That's a gun symbol option. Select that one and click on this one. That will be gone. Again, you are supposed to select this arrow, or else everything will once if you click anywhere, that will cut from this window. So now we have, this is a buffer. We'll try to simulate this one. So see now, I'm trying to simulate. First you should click on run simulation button, and it comes into the simulation mode. Now you try to give the inputs 1. If I give 1 here, the same output I need to get, because that's a buffering. Whatever the input is fed to into that particular one, the same output will be obtained here. So that's regarding the buffer. So then again, 0 0 1 0 1 0. So whatever the input you feed here, the same will be obtained at the output. So let us see the timing analysis for this one, timing diagram. See now here, you can see the timing diagram here. Just a minute, I'll yes, see now. Since first here the input is 0, whenever the input is 0, then the output also will be 0. If input is 1, the output is going to be 1. In the similar fashion, you are going to get the same output. Whatever the input you feed into that particular buffer, it will produce the same output. So for this design, now let us try to draw. Now let us try to draw the CMOS structure of the buffer. CMOS structure of the buffer. So first, I'll remove all this logical structures. And now let me take one PMOS and NMOS. First, let me connect the PMOS and NMOS in order to make it as a CMOS inverter. Both drains are connected here, and here both the gates are connected. Then use the VDD, that's the power supply, and try to connect it to the source of the PMOS. And the similar fashion, use the ground terminal and connect it to the source of the NMOS. So now, and we are supposed to even give the inputs. So this is your input part. That's a shorted gate terminal will act as an input. So use this button here, which acts as an input input terminal, where you can feed your input into this inverter. And then for this one here, output will be obtained from the shorted drain terminal. And here for this one, I need to again connect the same similar structure of the inverter. So again, I'll take another set of PMOS and NMOS and make the connection of PMOS and NMOS here. Both the drains are connected now, and now I'm connecting both the gate terminals. Now connect VDD and also ground terminal. So by using this wire, you make a connection of excuse me. With the help of this gun button, I have removed that wire connection between the two inverters. Okay, now you can find here see now, here you can find this small dot which indicates that electrical connection has been done between these two. So now this dot indicates an electrical connection has been done between these two inverters. And we are supposed to provide the output for this one second inverter. And now you use this LED light button. In this software, it is the option of this component is LED, which will act as an output. And now I have completed this connection of CMOS inverter with another CMOS inverter. It's like cascading of two CMOS inverter. Now I'll try to name all these components. First, input. Double click on this one. Put your arrow on this. Double click wherever you want to name it. Double click on that particular one. This particular window will pop up, and here you can find here pin name. In this pin name, you are supposed to give the input name. Input, and these are the different colors. In whichever color you want that particular output to be obtained. If you want, if you put it as blue, your output in the timing diagram, it will obtain as blue color. The input signal will obtain in this blue color. And you can here you can see that different generic names for that component is button 2 is given, and it is a user title is button. So these are the generic names, and you can even we'll use this one for the transistors. The name, now we have used the pin name. What is the pin name? That's a input. So after that, click OK. So now here the name of this particular component has changed. In the similar fashion, now for every transistor, try to change it. Double click on this transistor, P transistor, and select all these options. Select all this option, show pin name, show pin number, show symbol title, show name and properties. So then after that selection, you just try to click OK. And you can even see the generic name of the component on which you have selected. In this particular window, you can find the component which you have selected is a PMOS. So this is a PMOS which you have used here. PMOS, and these are the details about the PMOS. This PMOS has got 3 terminals: source, gate and drain terminal, and these are the fan in for the PMOS and fan out for the PMOS. I hope you know what is meant by fan in and fan out. Like regarding it talks about the number of inputs which you feed into the particular component, and also the number of outputs which come out of that particular component. That's regarding the fan in and fan outs. So now you can see, see this is a first terminal. S equal to 1, terminal 1, gate equal to terminal 2, drain equal to terminal 3. So these are the 3 terminals of the PMOS. In the similar fashion, now here you can name it for the NMOS. Select all the pins so that the different names of these terminals will be displayed on your screen. In the similar fashion, we'll do it for the next one also, next set of PMOS and NMOS. See here you can find terminal 1 of PMOS is a S1, S is a first terminal, gate is a second terminal, and drain is a third terminal. And for the second PMOS, in the similar way here, D3, D3, G2 and S1 for this NMOS. And you can even see now, if I want, see, I have got 2 PMOS over here. If I want to change, if I want to give the name for each and every device, then double click on that one. On the user title, here you can put it as PMOS1. PMOS1. So that is the name of this label of this one, PMOS1. Then next here, for the second PMOS, I'll name it as PMOS2. The naming of a transistor is very important. Why? Because while describing this one, if you have got large number of transistors, then you should be very particular about which transistor is acting in which with what kind of characteristics. So that's why you should be very you should name all the transistors. Then again, now double click on this output, and you can even name it as the output. So now we have completed the design CMOS structure of this buffer, and you can now run the simulation for this one. Run the simulation and put it on. Now click it on timing diagram. Sorry, excuse me. It's we have just run the simulation. Run the simulation and try to give the inputs for this buffer. See, whenever the input is 0, whenever the input is 1, you can see that whenever the input is 1, what is happening here? If input is 1, the PMOS will be turned off. There will be no channel, so there is no scope of VDD to flow from this source of the PMOS to drain of the PMOS. That's why we'll be obtaining an output of 0 over here, and that 0 will become as an input to the next inverter. Whenever it becomes this 0, which is obtained here from the first inverter, will become as an input to the second inverter. Because of that input is 0 over here for the second inverter, the PMOS is turned on and NMOS is turned off. So that's why we are going to get then it's a pull-up network, so where the VDD will flow from the source through the source of the PMOS to the output. So whatever the input you feed at the first inverter, the same will be obtained at the output of the second inverter. So that's why we call it as a buffer. It's a buffer circuit. So now let us see for the 0. Whenever you feed 0 into logical 0 into this one, you get an output to be logical 0. What happens at the logical 0? At the logical 0, the PMOS will be turned off. PMOS will be turned on and NMOS will be turned off. So the channel is formed over here. Since the channel is formed, the VDD will flow from this point to drain terminal. That's the output of this first inverter. So that first inverter's output is nothing else, but since it's an inverter, we have fed a logical 0 as an input. We'll be obtaining logical 1 as an output. That logical 1 will become as an output to this input to this second inverter. And since its input is equal to 1, the output which you obtain here will be 0. So this is how your circuit buffer circuit will be working. So see here, now I'm trying to give some inputs. Let us see the timing diagram for this one. See now, whenever the input equal to 0, the output is going to be 0. If input equal to 1, output is going to be 1. See here, we have even given what should be the color of our input signal while defining that input. So we have selected as a blue color, so that's why here the blue lines is obtained here. Blue color line is obtained. So whenever the input is equal to 0, the output is also whenever input is equal to 0, output is also 0. We can even see the detailed part of this one. Okay, it has taken longer time. Let me do it again. I'll show that one. You can see now here. So you can find it. This is acting as a complete buffer circuit. Whatever the input we feed into the circuit, we'll get the same output. 1, if it is 1, input is 1, output is equal to 1. 0, if our input is 0, output is equal to 0. So this is regarding the timing diagram of your buffer circuit. So now after this one, we'll try to generate the Verilog code for this buffer, and we'll try to, if you all are very much feasible with Verilog programming, then you'll be understanding how how to write this Verilog programming. What are this DSCH generates the Verilog code is it will be in the completely switch level programming. Switch level means you'll be writing your Verilog code in the form of a NMOS and PMOS. So see now, module first will be the module as per the syntax of Verilog. Module, then will be the module name, then the signals which are used for this particular buffer or particular design, circuit design. So module, and here the default it has taken the name of the module equal to example, because we have not set the name. You can see here in the top here, DSCH2, the name of this design which we have not set anything. So that's why by default it has taken example. The same name which you find here will be obtained in the Verilog code. You can find it in the Verilog code as a module name. So module name, input and output. Then among this one, these are the signals which we randomly write in that module in these brackets. but again specifically we are supposed to tell which signal is input and which is output. So input is a input signal, output is a output signal. So now among that one, which one we should specifically write about how the signal is moving from through which transistor and from which transistors to which transistor. Coming to the NMOS2. See, the first one is NMOS2. NMOS2 output. First, NMOS2 will be feeding an output. Then NMOS2 has got three connections here. So you can see, NMOS2 has got, the output of this one comes from this drain terminal of the NMOS2. Then again, the another terminals of the NMOS2 will be the VSS of this NMOS2, and also wire 1. Wire 1 is nothing else but this one, which you make here. Okay, so these are the three terminals. So so this is a NMOS2 output, and ground terminal, and wire 1 is this one now. This is the intermediate line. Yesterday in the CMOS inverter, we have seen one wire, but there we didn't specify a wire there because we don't have any kind of wire connections. But here there is a connection, intermediate line between these two inverters. So that will act as a wire. We should name it as a wire, and you should specifically you should write the name of that wire while writing the Verilog programming. So this is a wire W1, and this is one of the input to this NMOS2. Other input is equal to the VSS, and another output will be output, which we have named here. So that's why NMOS2 equal to output, VSS, W1. So these are the signals of this NMOS2. In the same way, PMOS2. For the PMOS2, what are the inputs? First will be input will be wire 1, another input will be VDD, and output will be output. So you should write this one in the fashion of first output, then inputs. So let us see now in the Verilog programming. PMOS2, the first one is output, another input is a VDD, then is a wire 1, this is a wire 1. So now the next for the PMOS 1, if you see the PMOS 1, for the PMOS 1, the inputs will be input, VDD, and output will be this wire W1. W1 will become as output for this CMOS inverter 1. So you can see now for the PMOS 1, output will be W1, this is this line, and inputs will be VDD and the input. So that's why the program has been written as W1 VDD input. And for the NMOS one, inputs will be input, this input, and VSS, and output will be W1. So it is NMOS 1, W1, VSS output. So this is how we are supposed to obtain this Verilog program for any of the design which you write it in a DSCH. Which so I'm naming this one now. Here in this module name, you can, it was earlier, it was a buffer. So now you can name it as a CMOS buffer for your convenience. And you can, once if you click this OK, this entire program file, the Verilog file will be saved in the DSCH folder. You can find that Verilog program file.